Cosmology and spectral action.
Good afternoon. Thank you very much. And I would like to thank the organizers, in particular Walter, for this invitation to this interesting workshop. So I will talk about spectral action in cosmology. And the outline of my talk is the following. First of all, I would like to discuss a bit the motivation. The motivation from point of view of mine, which means the motivation of somebody who is interested in early universe cosmology. Certainly there is a very exciting motivation from mathematics, from an elegant theory, but I will tell you what is that motivates me to work with that. Then, given the audience, I will just very, very briefly give you some elements of the noncommutative spectral geometry. You know everything about that. Fadele said a bit about that as well. I will tell you what I will need for the subsequent discussion. I see a couple of people who were not here before, so I can take that as an excuse. Then I will consider the gravitational sector of that theory, which for me is going to be like an extended gravity model. So I'm going to try to see what can I say about cosmology. This may be interesting from 2 points of view. From one point of view, because you will be interesting like that, to consider a gravitational model which goes beyond Einstein-Hilbert action, which you don't write by hand, but is motivated by a fundamental theory. And then, I mean, as a second kind of benefit, you will be able probably to put some constraints or confirm the validity or whatever of that theory. Now, in doing that, whenever I gave a talk in the past, and many of the results I will say here from cosmology is work that has been done quite some time ago. Nevertheless, I have been, asked the question from the audience whether this theory, which has higher derivative terms, passes the kind of linear stability. Otherwise, it has a negative energy modes, ghost, and that's a pathology. So we'll address this question. And then I will discuss some, let me use the words, shortcomings of this approach, in the sense that you just do a truncation and you throw terms which may be important in the regime where you want to use that theory. And then we have another proposal which I will discuss, and I will tell you the good and bad things of that. And then I will end with some concluding remarks and open discussions, from my point of view, of course. So motivation. Now today we have a very successful cosmological model. Classical cosmology is built upon two things: general relativity and the cosmological principle. General relativity is a classical theory. Certainly, it is correct for a certain kind of energy limit. We have tested, it's extremely successful, but you have to consider it most probably as an effective theory, and above a certain scale, you need to take corrections. The cosmological principle tells you that the universe on large scales is homogeneous and isotropic. This is certainly valid at some scale, but beyond a certain scale, then whatever you think about geometry loses its meaning, and you have to reconsider it. So if you want to go and describe early universe cosmology around the Planck era, around the Big Bang, you have to consider quantum gravity correction in your classical GR, and you have as well to consider the particular kind of geometrical background. Now, how do you do this quantum gravity? There have been various proposals. Usually they're divided into classes. You take string theory that tells you that matter is made out of one-dimensional objects, strings, open or closed ones. This theory has been shown later on to be much richer than what we thought originally. So you have these branes, a higher dimensional branes embedded in a bulk. Now here, matter is the most important ingredient of this theory. We can switch off all lights if you want. And then people who want to sleep, they will happily sleep. You see, otherwise you lose my nice blue background. Oh, this is very good. It's like in the movies now. That's very good. And then you have some non-perturbative approach to quantum gravity. Loop quantum gravity has been studied a lot. If you take the mini superspace approach of this theory, you have loop quantum cosmology. You might have as well in the framework of Euclidean quantum gravity Causal dynamical triangulation is a subject that has been studied and developed a lot in this university. And there you might have as well group field theory. Now, all of this the second class of models actually tell you that you cannot divide space to smaller and smaller places. At some point, you hit your quanta of geometry. And here, the bad thing, if you wish, is that the matter Hamiltonian is put by hand. So you don't take the interaction between your background and matter. Now, these are so-called top-down approaches. They lead to nice cosmological models that have been studied. I have been studying them. I work on that as well, but it's nothing to do with today's kind of talk and the meeting we have. Actually, last week, there was an interesting conference on this kind of approaches here in this university. And what I'm going to discuss then is how you can do a kind of early universe cosmology from non-commutative spectral geometry, which you can consider it like a complementary bottom-up approach. You get some data from the low electroweak scales. Your experiments work very well, and then you try to guess how space-time should be at large scales, at small scales, high energies. Now, of course, you might consider that quantum gravity near the Planck scale will tell you that whatever you know about geometry is not going to apply. But you might take the assumption, which of course one has to go beyond that, that if you are a few orders of magnitude below the Planck scale, then you can take these almost commutative manifolds. So in this approach, what is interesting and is completely different from the two classes I said before, is that you consider that the interaction between gravity and matter is really very important if you want to build the dynamics. If you take the string theory approach, you take the matter part. If you take the non-perturbative gravitation approach, then the matter Hamiltonian just added by hand. And here is the interplay between two. So that's the motivation, at least my motivation. Okay, non-commutative spectral geometry in a nutshell, because I believe the audience knows all that, but I will tell you at least what I will use later and where are the points that the subsequent work is going to change. So this framework, as you know, and at least one of the authors is present here, considers the standard model as a phenomenological model, which is going to tell you what the geometry of your space-time should look like, so at the end of the day you get the standard model action. So then you consider the simplest possible thing, that at every point of your four-dimensional compact Riemannian spin manifold, you have an internal space, which is non-commutative, which is discrete and captures these kind of standard model particles that you will have. So that's a kind of Kaluza-Klein of approach. Now, the four-dimensional compact Riemannian manifold is given by three objects: the set of infinitely differentiable functions on M, which forms an algebra, the Hilbert space of square integrable spinors on M, and the Dirac operator, which is going to act like an ordinary first-order differential operator on the spinors. And then you have the chirality operator and the charge conjugation operator. You do the same thing. This spectral triple is going to define as well this internal non-commutative space. And the most important ingredient is going to be the choice of the algebra. So now you have a 96 by 96 matrix, which would be the Dirac operator that Fedele was discussing before, which is given in terms of these two matrices here, S and T. T is a symmetric operator which acts only in the right-handed neutrino, and the S is given in terms of the 3 by 3 Yukawa mixing matrices. Now, the choice of the algebra, as it has been shown in this paper, is the product of the quaternions and k by k complex matrices, which the smallest, the minimal choice that you can make in order to be in agreement with the standard model is to take k equal to 4. Now, the physical space, therefore, that you have, the physical space that you have here is like if you have that your space-time is made out of two branes, each of them of 4 dimensions. This is the simplest thing you can do, but some time ago we have shown that this simple choice, it hides an important physical consequence, first of all, because it is necessary in order to this doubling of your algebra is necessary to accommodate the gauge symmetries, which you did, because at the end of the day you want to describe the standard model. In addition, it is related to dissipation, so you have loss of information. And if you used Hopf conjecture, you might at the end of the day say that somehow there might be some hints of the origin of quantization. And then least but not last, this doubling of the algebra is something that can lead to neutrino mixing, which of course you want for the standard model. Now, of course, to do physics, you have to write down the Lagrangian, and the Lagrangian that is taken is in the simplest way that you apply in this product space the spectral action principle, which tells you that the action is just the sum of the eigenvalues of the Dirac operator, which are smaller than a cutoff scale. Here you have two cutoff, a cutoff function and a cutoff scale. Of course, your operator is unbounded, so you have somehow to truncate, and that's the way that is done. And the functions that usually are used in the literature are given here. Is a function that indicates very fast for a large value of the argument. And then what you do, this of course is just the bosonic part, which I will take care later on when I'm going to do my cosmology. To take the fermionic part, then you have to add this term. And then what you do, you proceed with this Seeley-DeWitt coefficients, the heat kernel approach, and then you can write that your action is characterized by three momenta of the cutoff function, F4, F2, and F0, which physically are related to the cosmological constant, to the gravitational constant, and to the couplings at unification. And I will be able to constrain one of the three, namely this one, from astrophysical data. Now, this of course is an assumption to truncate and throw the other terms, is something which might not be correct exactly at the high scales where I want to apply this theory, and then it comes the proposal that I would like to make a bit later in this discussion. Okay? So, the rest follows with a calculation which might be lengthy, but it's straightforward. And the action at the cutoff scale, lambda, okay, the Euclidean action, it takes this form. You can see the terms that you know of. This is the Ricci, okay? Now, this is the Yukawa coupling for the top quark, the Higgs, the mass for the right-handed neutrino, the G1, G2, and G3, the three coupling constants. W and G and B are the strength tensors for the three interactions, U1 as U2 as U3. The A1, A2, and A3, actually, their values depend on the cutoff function that you consider, but is more or less of the order of unity. Now, this model, I'm not going to go through the phenomenology for the particle physics. It has been shown to be in very good agreement with the data, including the Higgs mass and so on and so forth. This has been done. Many things have been said. I'm not going to review them here. Half of the authors are within this room. Okay, so let me take then the gravitational sector of that theory. So I take the bosonic part of this spectrum, of this action, and then I'm going to say, okay, this is an extended gravity model where things are not put by hand, as often people do phenomenologically in order to explain something, they put things by hand, but it is set here. In other words, provided you have these conditions here, then that's how the action a la Wilson looks like. And there are some important terms that you can identify. You have the Hilbert-Einstein-Hilbert action with a cosmological constant, a topological term. Here is conformal gravity with this Weyl curvature tensor, and then you have conformal coupling. Xi is 1/12 between the Ricci and the background, between the Ricci and the Higgs. And therefore, at some point, I'm going to address the consequences of this coupling between the Higgs and the background. And whatever I'm going to say is valid for any theory that you have conformal coupling. An example is this one. Okay? So for me, this is interesting because here it is. I will take a model which is modified by a fundamental theory, right or wrong, this I don't know, but I will test if you wish. And then I want to build some cosmology based on this action where a priori things are fixed. Okay. So the gravitational sector of the bosonic spectral action and some cosmological consequences. Now, what is the approach and which are the negative issues in this approach. There is one that I haven't mentioned, which I will discuss just for 1 second. I will say. So the idea is the following. I consider the gravitational sector of the theory as an extended gravity model and address some cosmological questions. In doing so, I first assume that I can somehow, don't ask me how, pass to the Lorentzian kind of manifolds that we use in physics. Parenthesis, whenever I give talks like that in the field I belong more, which is theoretical physics, people accuse a lot about that. I mean, let's put a parenthesis, but that's a fact. Second one, whatever we use is based on this weak field approximation. Okay? The expansion that we made is valid if we assume that fields and their derivatives are small with respect to the cutoff scale. And the last but not least is a higher derivative theory, and then my question whether it has a linear instability. That's an old problem that has been studied. I will discuss that, and I will see how the problem is, there's no issue with that. I will discuss about this weak field approximation, and we'll have another kind of renormalization approach that I will briefly discuss. There is not much that I can say for the first issue, apart that this, as it was mentioned as well before, is something that you find it very often whenever you have a kind of quantum gravity approach with a path integral, you have this thing. People don't worry that much there. I don't see why we have to be that super critical here. And then, of course, least but not last, we have to keep in mind that we'll apply that in a context where you have to take quantum gravity corrections, and here whatever we say is indeed classical. So that's something that we have to keep in mind. There's not much we can do, but we have to keep it in mind. Okay, so basically what I'm going to do, I'm going to take this action, and I'm going to put constraint on this parameter alpha 0, which is related to the couplings at unification. Okay, here it is. And then I'm going to question as well what I can say for the role of my scalar field in the theory, which is the Higgs. Could it be the infrared, or what role could it have? I don't have fields that I can put by hand, so I have to see what I can make out of what the theory gives me. Okay, of course we know always that if we have an action, we can find the equations of motion. So here are the equations of motions. And you see this is Einstein's equation with some extra terms. And what you can see here is that I have defined this parameter delta CC conformal coupling, okay, which will become equal to 1 if the coupling between my Higgs and the background goes to 0. So usually you see in the majority of models, people put minimally coupled model. You put this thing equal to 0. Of course, it's a huge assumption. Whatever you take a quantum gravity correction, this will bring you away from 0. What value it will give you, I don't know. The theory has to give you. Now, there are many phenomenological models where people tune this thing by hand in order to find what you want to find. We don't do that here. The theory tells us that it's conformal coupling. So let us take that and see what we can make out of it. Now, in the simplest case, the low energy regime, where I can neglect the coupling between the Higgs and the background, then, of course, you find that the equation is going to become the same like standard Friedmann equation in an FLRW background, because in an FLRW background, what you have is that the Weyl tensor vanishes. So in order to find some kind of signature of this correction coming from this extended gravity model modified from noncommutative geometry, you have to take inhomogeneous and anisotropic backgrounds. At some regime, when you go to the high energy, you can no longer forget the coupling between the background and the Higgs. You have to take into account. And then what you see is that this coupling is going to play the role of an effective gravitational constant, or if you want to see the effect of the Higgs Lagrangian, you will see that it increases the self-coupling of the Higgs. That's the result. And by the way, these models have a similarity with compactified string models, or with what they're called in cosmology chameleon models, where the chameleon field here is the Higgs. So that's what I can make out of that. Now, I'm going to go to perturbations. So I'm going to try from some astrophysical data to put a constraint in this parameter F0. One of the three momenta is the one which is related to the coupling constants at unification. So I studied the propagation of gravity waves. Okay? So I'm going to consider linear perturbations around the Minkowski background. And the first constraints will come from binary pulsars. So this is the equation that you are going to have, the perturbed equation. If you take the beta going to infinity, then you recover the standard general relativity kind of results. And you have this conservation equation. So,
are you running the coupling constants?
No, I don't. I don't believe that it's correct to run the constants. Okay, and that's why I cannot do many more things than what I'm doing. So then we take the standard quadruple formula for the energy lost to gravitational radiation, and I have to calculate, this is the distance in the two binaries, I have to calculate the special component of the perturbation h mu nu, the tensor perturbation, and take the time derivative. This is a bit lengthy calculation, but after a few pages it's doable. And what we have found is that there is a critical value of the orbital frequency for which I found important deviations from the standard GR results. And this frequency depends on the cutoff. So there is a scale below which I cannot forget anymore what are the chances that I have from this extended gravity model. And then it's very simple. Then you take a bunch of binaries for which you know their location, the eccentricity, their period, and then you say I'm going to put a constraint on this parameter beta so that the deviation that I will have is going to be within the accuracy that you find the rate of change of the orbital period with respect to the GR kind of results. And if you play this game, you find a constraint, which actually is not very strong, but that's what it is, which, however, can become better with faster moving binaries close to us. Then we say, can we do better than that? So we want to calculate what we might have as constraint from the gravity probe B and the Lares experiments. We're supposed to measure the geodesic and the frame dragging kind of precession to a very big accuracy. So again, what you do, I will go very briefly what you do. You write the equation of motion for the gyrospin 3-vector S. This is your metric, okay? And phi and psi are what they are called the Bardeen potential, what they correspond to the gravitational perturbations, and A is a vector potential. Then you go and you split the gyrospin 3-vector. So it is given in this way where I have written it in the terms of the geodesic precession and the frame dragging precession. And then you go and you split, for instance, the geodesic precession in two terms. One that comes from general relativity and one that comes from these extra terms that I have in this extended theory of gravity. And then I'm going to say that this has what the theory tells me, and then the constraint, the new term, has to be much smaller and has to be what is the accuracy of the experiment. And then you do the same thing for the frame dragging precession, and in both cases, the constraint that we found still is not great, but is better with what we had before. The strongest possible constraint we have found comes from torsion balance. In other words, we have observed that the modification that you get from this noncommutative spectral geometry action, from this extended gravity action, to the Newtonian potentials phi psi that I had before, have the same kind of form like if you had a fifth force with this potential, okay, where lambda is the inverse of beta. But we have constraints from lambda. There was an Irvine experiment, constrain the lambda, and therefore I can constrain the beta, so this beta is related to the coupling constants at unification. So it's amazing how from this kind of results I can constrain one of these three parameters, and I believe that we cannot have a strongest constraint than that. Okay. Next thing, yes?
Yeah, so you could also, the G, so the G3 and so on, they're related to
Yes.
F0 as well.
Yes, exactly. Yeah.
Is it compatible or?
I believe, yeah, it's compatible with that, yeah. But I cannot constrain, my problem is that I cannot constrain anything else, like the F2 and F4. The only thing that I constrain F0, and this is important exactly because of that, because it gives me a relation which is consistent, you're right, with the things for G. And yeah, but that's it. Unless I want to start running with that, which I believe is wrong. So since I cannot do that, then I'm stuck. I cannot do much more. So then the next thing that we said, okay, can we find this, people like to okay, I mean, given that the audience is not.
What do you mean when you say you think the running?
I mean, this at the scale lambda, this valid, and this, if this valid, this is the axiom. I cannot say that these ones, they would be the same at a different lambda, or they will be the same, they're going to run with lambda. I don't think that this is correct. I mean, I don't know if people in the audience have a different view, but I think that the correct thing to say is I have this in a cutoff scale lambda, which is supposed to be the gut scale because of the the conditions that we get for the couplings, which are the same for the various gauge models. Then at the gut scale, which is the lambda, these conditions hold, and provided these conditions hold, this is my Lagrangian at lambda. I don't know how this will be in a different scale. That's all I'm saying. So I cannot run this one. They don't run. There are papers in the literature that they run this. I'm not convinced that this ansatz, because it's an ansatz, is correct. So I'm not doing it.
Everything except the cosmological, which is quadratic hypothesis, and also the Newton. So these are the difficulty.
Yeah,
Some
but
people believe they don't. For example, Newton that doesn't run much.
yes.
Cosmological.
No, but for instance, you can. The question is, can this run? The conformal. And there is a paper ages ago from some Japanese people who say that if it is equal to, if it's not conformal coupling, if you take quantum gravity corrections, it will never become. So therefore, this seems to be like a fixed point. If you have that, you cannot go away. So you cannot run with this.
You can run everything. Whether you can trust your answers is the.
But that's a question. If I cannot trust the answers, what about?
You can trust actually everything except the Newton and the cosmological. The rest you can trust more or less.
Yeah, but then is exactly.
The mu zero.
Yeah, but I don't care for this mu zero square.
The
What?
mass also.
Yeah, but for me the interesting is to be able to put a constraint in one of the three momenta. If I cannot run for these three momenta, F0, F2, and F4, then that's it. That's where I can extract something. In other words, the coefficients that they will appear in my axiom. If I cannot play with that, then I don't. Okay, so given that the audience is not in cosmology, let me tell you for 1 minute or so that I mean. It seems to be that, standard Big Bang theory, which is based on GR and the cosmological principle at some point cannot explain you the data. So that's the way that you take a coupling between relativity and particle physics. You take the existence of some scalar fields with some particular kind of potential, and you say, in order to somehow freely this acute dependence on initial conditions of my model, I have a period of exponential expansion, which is called inflation. And then people take an inflaton field, as it's called, with a particular kind of potential. Now, I have my second thoughts about this thing, because if you replace something with something else, this something else has to be generic. If it's not generic, there's no point to going all this kind of machinery. So I will come to that later on, but it seems to be that people want to have an inflationary field, and then, of course, we know a scalar field, the Higgs. We didn't know for years, and we have been using it. Now we know it exists. So then the question is, could the Higgs field be the inflaton? So here, if it's minimally coupled, then it has been shown that cannot be done. Here I have conformal coupling. Can it be the inflaton? In other words, can I find a region where my potential is flat enough to give me my slow roll? So we have examined this case. And what we have shown for a conformal coupling between the Higgs and the background, example this one, considering up to 2 loop corrections in the potential, for any value of the top quark mass, there is a value of the Higgs where the potential is sufficiently flat so that it can give you inflation. So far, so good. So I can have inflation. Now, in order to have sufficient inflation, you need what is called the number of f-folds to it about 70. So inflation has to be last enough. To be last enough, it's going to give you constraints on the form of the potential. And the form of the potential, it is captured by its first and second derivatives, which are called the first and second low roll parameters, eta and epsilon. So in order to have sufficient n, the epsilon, for instance, has to be small. And then that's where the problem appears. Because that means that in epsilon to be small, then the result I get for this quantity, the value of this quantity is known from the CMB data, is completely different from the one that the theory tells me. So even though I can accommodate inflation, I cannot meet the results of the CMB. So I have disassociate the inflaton field from the field that is responsible for the density perturbations and structure formation. Parenthesis, this is valid for any conformal coupling, which means that this is valid also for the sigma field that has been introduced. And now if you have heard talk saying, oh, the Higgs field can be the inflaton, the Higgs field, parenthesis, nothing to do with noncommutative geometry, has been shown to be successful in agreement with the results from the data for a coupling which is huge, 10 to the fourth. Then you have to come and tell me which is your model that gives you a coupling of 10 to the fourth, because usually the couplings are of the order of 1. So here it comes. Here is a model where I cannot play and tune the parameters. If you hear that, yes, Higgs inflation can pass the test, yes, but with a huge price to pay and with a coupling that I don't know where it comes from. Okay, so now, of course, there is a question, could I have a Higgs, would I have an inflaton field here? Maybe, because it has been suggested a long time ago, you could promote this lambda thing here into a field, okay, in this way, and then the sigma field, a dilaton field, could play the role of the inflaton. I don't know. This is the corresponding gravity Higgs dilaton kind of Lagrangian, and then if you know what is the potential of this field, it could be the inflaton. I don't have an answer to give you because I don't know the form of this potential. So that's about that. Then, I promise that I will say 2 words about the linear stability of the bosonic spectral action. So the question that people address is here is you have a higher derivative theory. Higher derivative theory usually it's plugged by the existence of these pathologies. You have a negative energy mode, so you have this ghost. What's the issue here? So the first thing that we did in order to address this question, we consider the simplest case, that you consider in vacuum spectral action within a 4-dimensional manifold with torsion. With a particular type of torsion, it is antisymmetric and is such that the curvature tensor that you will get is going to have the same asymmetric properties as the Riemannian curvature tensor. And then we use the trick that was highlighted. I mean, this has been addressed in this paper here. That if you vary all the connection fields and not only the metric, then the 4th order equations of motion that you get, combined with the Bianchi identities, they will bring you back to 2nd order Einstein's equation in vacuum, provided torsion vanishes. So far, so good. But what we care is for the cases. So we applied and we found this result. But then the next thing is to take really almost commutative geometry. And then the things are not so straightforward as before. Because it happens that we have fermion fields, of course, and the scalar fields. And then the integrability condition that we had before cannot be applied. So here what we did, we wrote down the Hamiltonian, and we have shown that the Hamiltonian is bounded from below, and then we can secure that this higher derivative theory that we use in order to do cosmology indeed is not plagued by the Ostrogowski instability.
Is that lower bound just because of the cosmological constant?
No. No. Now, the last thing that I said, I'm not sure whether it's a strong word to say shortcoming, so don't take it take me wrong, but anyway, is a kind of critic or whatever, of weak point that we have seen. Remember what I said before. We take this weak field approximation. So this is the action which it is written down, where you use this asymptotic heat kernel kind of expansion. In other words, you keep, you keep is the sum of the eigenvalues of the Dirac operator smaller than this cutoff scale. You keep these three terms, you throw everything else, but this approach can lead to a divergent kind of result, which certainly you might expect that it cannot be the same with the spectral action. So about, what was that, a year ago, we suggested another way of doing. So we proposed, instead of what, let us call it the cutoff spectral function we had before, let's say the zeta spectral function action, which is defined as the 4 coefficient of the corresponding Laplacian operator, which is well defined. Then what is good is the following. There is a very important role which is played by this dimensionful constant m, which appear in the Dirac operator, because the existence of this term is actually what is going to give these lower dimensional operators that we have there. Certainly, it's not correct to say that the spectral action will give us the value of these A1, A2, A3 coefficients, okay? And the values at the low energy regime, they have to be taken by phenomenological data, okay? So usually you normalize them by hand. Now, what is good in this approach is that only the terms needed for the standard model and Einstein gravity appear, and therefore we have an exact result which does not depend on this cutoff, that the cutoff on the scale and the cutoff function. The cutoff function is not very important, but the cutoff scale is more important. Now, let me make a comment about that. In order to get in the UV normalization the Higgs quadratic term, then you need at the proper position in the Dirac operator to put a term which corresponds to the neutrino Majorana mass. And actually this term seems to be also necessary in order to get the correct experimental mass of the Higgs. Now there are two ways that you can do that. You can introduce a term like that, and then what you are going to get is that the zeta action is not going to have the lower dimensional operator, so you are not going to get the quartic Higgs, the gravitational constant, and the cosmological constant, and somehow you have to come up and to dynamically generate the scales. If you can do it, this is great, because you can get everything without putting anything by hand. We haven't done it yet. Now, this approach seems to be the one that comes if you consider this grand symmetry framework. But there is another way that you could do so, is you could introduce these constants, okay? And now these constant mass terms are the ones indeed which you need in order to go and have this dimension full 3 quantities that we want. If you take this approach, then that's how your action is going to look like. And what is important to note is that these constants mi, they can be as small as you wish, but they have to be non-zero, because that's the way in order to go and introduce the counter terms which you need, so that in the UV normalization you can have the Einstein-Hilbert term, the quadratic Higgs, and the cosmological constant. But no matter which of the two approaches you want to use, one or the other, at the end of the day, this zeta spectral action has no higher dimensionality operator, so we don't have the problems we had before. You don't have asymptotic expansion issues, so it is convergent, your theory, and it is purely spectral. Now, in addition to that, there is another benefit that you can have. If you go to calculate the spectral dimension in the standard, the standard approach of the cutoff spectral action, then what you find is that for all spins, the spectral action vanishes, which may be the artifact that you take a classical action and you apply it in the kind of Planckian kind of regime. Of course.
Can you go back? It's clear what you're saying that the Dirac operator by MI. So
Yes.
di goes to di plus MI.
Yes.
What you are saying essentially is that I would like simply to consider the spectral action only with the A4 term.
Yes.
Now, obviously, if you shift the Higgs field, so obviously when you say d goes to d plus m, you have shifted essentially the Higgs field by a constant. So if you look actually at old spectral action, in which you have h, so essentially if you put h plus m, you know,
Yeah.
for example, r squared term will give you the r term, and the h will give you the m squared r, and things like that. So you can generate actually your action from the spectral action, cutting it at only A4 by the shifting. Is that correct?
I believe. But then what are you doing with the expansion? The expansions, what are you doing with your terms, which I don't have? In my term, we don't have higher than 4. What do you do with that?
Sorry?
In our approach, we have that. In the approach that you say, you have the higher...
The function vanishes, has all derivatives.
but that's an assumption, which we don't want to make.
But you made the difference.
No?
You define the action to be limitless as equal to 0. This is it's equivalent assumption. You know, you fixed your
Yeah, but
function.
we don't
D
know.
minus 2 you've already fixed the function.
Yes, but...
So it's the same. There is an assumption that take a function of f so that all derivatives is a constant function. So all derivatives are 0. Now you say, okay, I don't want to take that. I will take a function which is given by x to the power minus 2s or x to the minus s.
Yeah, for s equal to 0, I have no poly, have nothing here. Yeah, exactly.
It's you replaced one assumption with another assumption, but you have a further assumption which you shifted.
No, I don't have a further, because what I'm saying here is you can take this approach or you take that approach. If you take the one where you shift it, this is your action. If you take the one, if you take the one which you don't shift, I don't have the Einstein-Hilbert blah blah blah, which I have to generate them dynamically. So it's up to you. So if you don't want to put this mi thing, the constant, that's the action, which is fine by me. In a way, it's even better, because if we're able to dynamically generate these 3 terms, then we have everything from the spectral action. Exactly, that's what I'm saying. I don't have no dimension 0 at 2 operators, which means that dynamical generation of the 3 scales upon quantization is to be done. If we're able to do it, then I think this approach is stronger, because I get everything from the spectral action. What? Yeah, but I still have my...
But the term that we add corresponds to the neutrino masses again. So the term that we add is basically the only term that you can add, because it's the neutrino mass term. So as for deciding to have a residue or a function which is a cutoff, okay, yes.
It's a choice, it's a matter of taste. It's a matter of taste. Okay, so... But I will be grateful if we can come up and discuss on these things, because for us are important, and I mean, this feedback is really, very positive. Okay, so if we go to calculate the spectral dimension in this approach, then since in the same behavior in the UV infrared you find for the Higgs scalar and the gauge fields, then the spectral dimension is the topological one equal to 4. If you take the gravitational spectral dimension, then of course, due to the effect to the existence of the 4 derivative terms, that you find it equal to 2. And of course, there is a limiting kind of case in the middle scale where these extra terms are not important anymore. They don't play an important role. And then this low energy kind of limit, we go back and we find that it is the same like the topological dimension of the manifold. Open questions and concluding remarks. I would like to just summarize everything. Non-commutative spectral geometry aims at explaining some conceptual issues of the standard model, whilst it offers a geometrical framework to address physics at the quantum gravity regime, following the approach that the interaction between gravity and matter is the most important ingredient to define dynamics. In particular, non-commutative geometry aims at defining the non-commutative algebra of observables of a quantum gravity theory. And then what you find in this approach, if you put together the standard model and gravity and kind of Kaluza-Klein kind of space, and you use the well-known experimental results at the electroweak scale, you can you can guess how it could be the structure of your space-time at the very high Planckian almost energies without putting any kind of ad hoc proposal. So we can say that this approach offers a very elegant, a purely geometric interpretation of the standard model coupled to gravity. So to me, this is extremely nice result. By construction, your theory lives at the gut scale, so it can give me a framework in order to study some cosmological questions. Then I apply the spectral action within an almost commutative manifold, and of course, once we have to go beyond that, okay? And then you get gravity with the Young-Mills and Higgs. Now, assuming that we can pass to Lorentzian signature in the context of the cutoff spectral action, then take into account that you have this weak field approximation. We have found some constraints in one of the 3 parameters, and we have examined the role of the inflaton field, of the Higgs field. Then if we go to this other zeta spectral action approach that I discussed before, we might cure these issues, but then we have to come up in some way and generate these dimension-full quantities that we need. The open question remains inflation. So neither the Higgs nor the sigma field can lead to successful inflation. And you know, my personal view is that I don't like these things that they are put by hand. And this, as a comment, it seems to be that it's difficult to construct an inflationary scenario within a particle physics model. And about 2 years ago, we have studied all the Higgses that bring you to the SO10 down to the standard model, trying to see whether any of these could play the role of the inflaton, and we have found that this is not the case. You have to put it by hand, which to me seems that this is not very natural. But that's how it is. And of course, I would prefer that instead of doing that by hand, I have some extended gravity model, some corrections from quantum gravity that can play the role of a scalar field with a given kind of potential. And that is very successful, the Starobinsky model. So that's what the Starobinsky model tells you. You have Einstein-Hilbert R plus an R square kind of term. Okay? And it has been shown by Starobinsky long ago that this is conformally equivalent to a kind of canonically normalized scalar field with this type of potential. And then, in order to be able to meet the data, there is a constraint in this parameter in front of the R squared term, and it requires, actually, that this term is really very big. What it happens in the case of this extended gravity model that I discussed, you have the Starobinsky model works even if you have 0 cosmological constant. So here we have the R, but too bad, we have a C square as well. And remember what I said long ago in this talk, that if you take an FLRW background, the Weyl tensor vanishes, which means that here, unfortunately, the Starobinsky inflation cannot be applied. Now, open questions in this inflation. Could be a scalar field in a beyond the standard model approach. There's something to be seen, and we discussed a bit with Walter recently. I have this open question though, because long ago we have studied all the symmetry breakings, bringing you down to the standard model. And by studying the homotopy group of the false vacuum, we consider what kind of defect we might have. And if you have a defect that you don't want, for instance, a domain wall or a monopole, you have to put an era of inflation. When you see a 1, that means that is a monopole. If you see a 2, is a cosmic string. Okay, if you did 2 prime, is embedded cosmic string, which are very good. So which means that somewhere here and somewhere, so in the last symmetry breaking, where an undesired defect is formed, I need to put an era of inflation. But then we have seen that if you take this kind of symmetry breakings down to the standard model, none of them could be the inflaton. So I don't know. This is something that we have to question, whether here this inflation can be any of these fits that you have. And then, of course, in this grand symmetry approach, there might be other scalar fits, which I don't know what they are, and we could see their fitting. And of course, is the question about the dilaton fit that could play the role of is to be seen. And of course, it can be that there are some other kind of you go. Away from this almost commutative kind of geometry, and then you might have corrections that they can give you the terms that you want in order to not to need the role of an inflaton field to be accommodated to solve your problems. Thank you very much. I'm not going to pronounce that in Dutch.
Okay, so we have time for some discussion.
About this generation of these lower dimensional terms, with phi squared, for instance, they're always with the positive sign. So you generate plus m squared, phi squared, or h squared.
Yes.
But you still are interested in Higgs mechanism. You talked about Higgs
Yeah.
absence. How do you argue that it's going to become negative? Negative mass.
Once you counter there,
You put it,
it will be also negative.
which means you put it by hand almost. You put it by hand. I mean, in the standard way, it is done like that. It is put by hand. The whole idea if we could go beyond that.
For the spectrum, actually, the is actually negative.
Because you're expanding E minus
Yeah.
x squared.
If
You
minus
get
phi
1
squared,
minus x squared plus x2.
It has the right sign, but the value is put by hand.
it's positive because f is positive function.
I suppose function.
No, the quadratic term that you put in the Higgs potential, it comes by hand. You just put it by hand.
E to the minus.
You are expanding it a little. If you expand e to the minus x squared, you get 1 minus x squared plus x to the 4th. This alternating, you go to the x6, there's really
Yes,
minus.
but I
And
think.
it's not by
Yeah.
the function is positive, so this
Yeah,
is multiplied by
I
positive.
think that one by one the terms are fine, but if you take all the terms together, it's not going to work.
Why?
That's how I convinced myself. I have to issue the calculation that if you have one by one the terms, it's fine. But if you say the sum of the terms, then it's not going to give you the minus sign.
Actually, 1 comes with lambda squared.
It is because, as I think, to me it was a mystery. If you go to you are really it's heat kernel expansion
Right.
based on Taylor expansion of the exponential function. And it alternates. That's why it plus, minus, plus, the cosmological constant.
Yes, but then you assume that the coefficient of the other terms is that you.
If that is a positive function, then all these functions will be positive.
And actually, the one which is negative is lambda squared. So it's actually.
There's a reason for it. It's not random.
Okay, let me double check and we see.
I can make a comment about a possible scalar field.
Oh, please, yes.
In the new work that I did with Alan and Mukhanov, we, with this quanta, we
Yes.
have these mapping fields.
Yes.
And the question arose is, if you want to do it Minkowski, with Lorentzian signature, and in that case you have to start from free geometry then you map with 3 fields.
3 fields.
And there is one extra field which will be the time direction. And that actually discovered really gives a condition which is like the inverse of the metric G mu nu, d mu x is 1. Now, in a different work with Mukhalaf, which we did earlier, we discovered that this condition on the Einstein action generates what we call mimics dark matter. So, and this same field, once it gets the potential, it really gives
Could give you.
And we have shown that it gives
I gives inflation.
Yeah, so we've written, but these the
It's
work
shifted,
there
yeah.
are independent of this work,
Yeah.
and this condition came out. We didn't write the paper yet, but indicated it is there. So I think in the end of the day, there will be a scalar field that will give you inflation, and the models will.
But it dependent on all these fields we discussed now. It's
the same, but there is an extra condition that came, which that you have mapping field X, and
Yeah.
it's constrained, but that doesn't constrain gravity.
okay.
It
Okay.
makes
So
it a bit more general and allows dust to come out free of charge,
okay. Okay.
And so this field actually is not a new field. It substitutes one of the metric components, which is time. So this field becomes time, and it gives a potential which is function of time, and then you can get
You can get it.
cosmological model, and it works really very well. So this we have written papers where it's called mimetic dark matter and cosmology with mimetic matter.
Okay. I have a look. I have a look.
So hopefully it will be accommodated.
I have a look. Okay.
Just because how much do you mimic that matter? Meaning that all these Planckian dreams are very well, but what about present-day cosmology? What about collision of galaxies? What about all the
Well,
rotation
actually,
curves of
it
galaxies?
simply mimics dust. So it assumes that all the dark matter that's present in the universe is dust, and it is just gravitational interactions. And that's it. But it changes the problem to an initial condition problem. That's it. Doesn't solve the problem. It transforms the problem.
But the idea today about the dark matter is that it's called dark matter, and therefore you don't have any of these important interactions. So I don't know how it's going to work.
It interacts
Yes,
very weakly. So
weakly.
if it's there, it simply gives
Yeah.
you bulk. It's dust. So there is no
Okay.
contradiction there.
Dark matter, though, not dark energy. Dark matter. We
Yeah.
don't have
For
dark
dark energy, that's a different, that's a different solution. That's not contributed. I don't know how it would fit.
matter. Okay.
Okay, so any other Oh, question over there.
Do you get any constraint from the recently
No, because I mean they cannot. They're extremely. No, because yeah. Will not do for that, and it's also true that once we got the strongest limit from this fifth kind of force, then I don't think that we get anything, better from that.
Okay.
But it's true that there is the quadruple formula, which is not going to be valid at this regime. So